smart contract certification in COC, and Danil Annenkov will give the talk.
Hi everyone, I'm going to talk about a smart contract verification in COC. And of course, before I start talking about smart contract verification, I'll give a little bit of sort of intro what smart contracts are and start with what smart contracts are not. So maybe you already heard about smart contracts for blockchains, but this concept was introduced some time before, and the current sort of incarnation is not exactly what the concept of smart contracts was meant for, introduced in 90s. So we usually think of contracts as some kind of specifications of obligations, some sort of like a declaration of obligations. It's not exactly what smart contracts for blockchains are currently, and how Fritz Henglein concisely put it, smart contracts are neither. So what they are then? So it's completely safe for sort of kind of think of the purpose of this talk. Smart contracts are just programs in some general purpose programming languages running on a blockchain. So the specifics comes from the sort of environment where they run. And let's sort of unfold a little bit this definition, running on blockchain. So for the purpose of this talk, you can think of blockchain as a append-only distributed database. And these smart contracts are sort of like some fancy stored procedures for this distributed database. So the code is recorded in blocks, and calls from users also recorded in blocks. But the state of the contracts is not recorded in blocks usually, and maintained by each participant, each node participating in the network. So each node is responsible for executing these calls coming from users and maintaining a state. And so contracts can call other contracts, and this is also sort of important to emphasize. And these contracts can be arbitrary, so they contain arbitrary, possibly malicious code. And also the popular misconception that contracts are some kind of self-executing entities. So they are not. So they are procedures recorded somewhere, but someone has to call them to start execution process. So what is so specific about smart contracts? Why we want to verify them? So usually, I mean, there's a lot of value in smart contracts because quite often they manage money. And this is one of the sort of common applications, some auctions or crowdfunding campaigns, or so people send out their money, and there is some sort of program that manages how to send this money to according to some conditions. And so once deployed, this smart contract cannot be changed. At least there is a good solution for that currently. So you have to, well, better if you get it sort of right from the first attempt. And according to the code's law principle, there is no third party that can resolve some issues arising from execution of contracts. For example, when something went wrong, well, sorry about that. I mean, this is how it was programmed. And we already know that examples where the huge financial losses happened, the DAO hack, and sometimes it's not due to the hacker attack, really. So there was like a bug in library code, and that led to a lot of money being stuck on the contract without being able to interact and get them back. So we would like to focus on sort of a subset of smart contract languages, specifically on smart contract languages employing the functional programming paradigm. And so in this case, you can see contract as a pure function, roughly with this signature. And here also the fact to emphasize. So basically, it's like a state transition in a sense. So it takes current state of the contract and produces the new state. And also, it expects some messages on which a contract can decide what to do. And call context with additional information. So the amount sent, who calls the contract. And it results, as I say, in new state and the list of actions, which can be transfers from account to account or calls to other contracts. So but you can see that I'm not telling the whole story here, because blockchains are stateful, right? And I say, oh, it's a pure function. So we need a little bit another sort of piece to be able to update the state. And this is something called a scheduler. So basically, the state update after executing this function happens by calling by the scheduler. And also this list of actions also is executed in some order by the same piece of software. But I think it's a sort of a good step already of separation of concerns of the contract itself, and the scheduler that takes care of executing the actions and updating the blockchain state. So a bunch of languages. I mean, this is not by no means a complete list of languages. These languages follow specifically this execution model. There are other languages which don't, and so they're not sort of listed here. And we're going to focus on the ACORN language developed at the Concordium for the Concordium blockchain, and so that's what we sort of going to verify. And so what is ACORN? So as I said, it's smart contract language for the Concordium blockchain, and it's explicitly typed a system F2 with inductive types and general recursion. And so this is another thing sort of to emphasize here, that ACORN is basically directly executed by the Concordium infrastructure. So this is, you can say that the ACORN program that's what is going to run there. And that makes it good target for verification, because this is precisely basically what's going to be executed. So first of all, what do we want to do? So we want to reason about meta theory of our language usually, right? That's why, for that purposes, one usually uses deep embedding, which is like inductive type in COC, and then you define whatever semantics you want, like interpreters, static semantics, whatever relations you want. But there's also, we know that our language is functional, right? So, and COC also has Galena, is a functional language. So what we would like to have also some way of converting our functional programs, smart contracts, to Galena programs, and well, that would give us a very convenient way to reason about these programs, because well, it's more or less clear how to verify functional programs in COC, right? It's sort of more convenient than going through the deep embedding. So that's why, so we want to combine the two things in some sort of sound way. And for that purpose, we define something called lambda smart, which is explicitly typed system F, essentially with inductive data types and structural recursion. So you can think of it as a, well, fair subset of ACORN or pure subset of ML-like language. And also, we use MetaCog to, this is our deep embedding, right? This is an AST. And we use MetaCog to produce a shallow embedding, a COG function out of expression in lambda smart. And we also prove soundness of this embedding, of this transformation procedure, using, again, Cog's meta theory formalization provided by MetaCog. So I'll say about MetaCog a little bit later. And also we integrate, so this shallow embedding gives us a function. And we integrated our shallow embedding with the execution model that takes care of executing contracts and sort of maintaining the state of blockchain. So we can reason about like smart contract specific properties. So what is MetaCog? We already heard a little bit on Katrine's talk. So it's a metaprogramming framework for COG. And so many sort of sub-projects are united by this name. And specifically relevant for us is template COG, which provides a quote-unquote functionality, which is similar if you know Lisp. So it's similar but typed. So most relevant for us is unquote. So basically we take a well-formed, well-typed AST, and we can turn it into COG definition. So this is what we're going to use. And another bit which we're going to use, it's formalization of Cog's meta theory, something abbreviated as PQUIC. It's a polymorphic cumulative calculus of inductive constructions. And we're going to state and prove soundness theorem using this formalization. So this is like a big picture of our framework, and I would like to guide you through sort of the process of taking a language expression and going all the way to the sort of proving properties of it. So we start here with AST of language we want to verify. Currently we support ACORN. And from this, we print an AST in our lambda smart in deep embedding. So once we have this, we can apply a translation function, which you can think of as a compilation procedure from system F plus inductives into calculus of inductive constructions. So once we get here, we can use unquote functionality provided by MetaCog to produce a shallow embedding. On this shallow embedding, well, this is a regular COG function, so we can prove function correctness properties in the way, or in a convenient way. with a little bit more of work, which is mostly automated, basically just to have a signature that matches something that this execution framework expects. We can feed in our shallow embedding to the contract execution framework, which takes care of executing of these actions potentially produced by one-step execution of the contract, and prove something about interacting contracts, some safety properties, and so on. And here, since we have this translation, I have a meta-theory formalization of COC in COC itself. We can state and prove soundness theorem, and currently we have computational soundness, and a bit of meta-theory for lambda smart is given by the definitional interpreter. So here's just a simple example. We take this code in ACORN, which is, well, it's a fold right. And so the ACORN parser gives us an AST, which we print in this form. So this looks like a mess, and it should look like that because it's an AST of, well, something. So it's an AST in lambda smart. Then afterwards, we can apply our translation function and run it within a template monad. This is also provided by MetaCog, so this is a monad allowing you to interact with COG's global environment. So this function basically translates this AST into MetaCog AST and unquotes it and adds a new symbol into your environment, and then you can interact with it. So you can print folder, for example, and then you get, this is a COG function, the corresponding COG function. So here now it's accessible for any lemmas you want to prove about that. And then you can prove, for example, this fold right is exactly as fold right is defined in, well, extensionally equivalent to fold right defined in standard library of COG. So this gives you some way of verifying. So standard libraries for functional languages, not necessarily smart contract languages. And as I said, we state and prove soundness theorem. So for our translation from lambda smart to Pickwick, and it basically says that if our interpreter produces some value, then there exists a derivation in call by value big step evaluation relation of MetaCog for the translation of this expression to appropriately translated value. So currently we support only structured recursive programs because this is what you can embed in COG, and our focus was on producing shallow embedding. And we rely on the unquote mechanism of MetaCog is correct. But so this is not about this theorem because this is just produces an AST, right? But still, this is like a next step after we proved that. But the unquote is supposed to be like a basically one-to-one function mapping kernel representation in MetaCog to actual kernel terms in OCaml in COG. And they're really supposed to be one-to-one, and they mostly are. So the MetaCog may be a little bit simplified. So it's like a very simple and sort of a very small piece of code. So now a little bit about the execution model. Remember I said the contract is something like well, it's a function roughly with this signature, and it produces this state and list of actions. So I haven't said much about this list of actions. And these actions can be transfers, called to other contracts, and maybe even contract deployments. So the idea is that this function, it does not modify anything, right? It's really a pure function. It produces a list of something that the scheduler should take and then execute, probably updating the blockchain state and maybe calling other contracts. So it may result in a tree of executions, really. And so the idea is that this execution model formalizes the scheduler, and there are more details in this paper, smart contract interactions in COG. So we basically integrate whatever comes from our shallow embedding. We integrate it with this formalization of the scheduler. And this scheduler takes care of maintaining state. And then you can actually reason about how your contract interacts with actual sort of with the model, at least, of a blockchain. And basically, it provides a reasoning framework on traces, which means you can state something like starting from some initial state, your predicate holds for all reachable states. So like something like the safety property of your contract. And also, I mean, this is you can't prove really with just functional correctness properties of this function. Something about like how, for example, if you have two contracts which send messages to each other, so this needs to be formalized using the scheduler, because this is how interaction happens in this model specifically. And this work contains an implementation of improve partial correctness of the Congress contract, which is simplified the DAO contract, and was this sort of well-known hacker attack on the DAO contract, and the main problem with this contract was reentrancy. And this framework, the execution part, allows to reason about this reentrancy problems for smart contracts. Okay, so more sort of I showed you a little bit of like just functional programming code, and of course we also sort of benchmarked our framework as verifying properties of smart contracts, and specifically we verified a crowdfunding example. Basically, it's a smart contract allowing arbitrary users to send in some money, and within certain deadline and certain goal should be reached. If goal is reached, then of course the money can be transferred to the owner of this contract. If it's not, then people who donated money can potentially get them back. So that's what we sort of asked in our framework. We stated these lemmas, proving properties whether people who contributed to the contract can get money back, and that some functional correctness properties whether contributions are recorded correctly, and does the contract has enough money to sort of reimburse back money to users if the goal was not reached, for example, and a bunch of other properties. And here's how it's stated roughly. I mean, this is a lot of code, I understand, so don't sort of worry about, too much about that. But the idea is here we state exactly sort of this property if the contract has enough money. And it says that account balance, this is sort of the actual account balance maintained by a node, a blockchain node, is greater or equal than the sum of individual contributions of the people sort of participated in this crowdfunding campaign. And this CF contract thing, this one here, we say that it's deployed in some address. Now, so this CF contract comes all the way through our framework, starting from deep embedding, through the translation, through the unquoting. So we have an actual sort of function, init function, receive function, and we reason about it in the execution model. So in conclusion, so I presented a framework allowing to combine deep and shallow embeddings. And we proved soundness through the formalization of meta theory of Koch. And we demonstrated some, so we verified some bits of standard library of ACORN, written in ACORN language, and also proved some examples, contract examples, specifically crowdfunding example. And we integrated this bit, the embedding bit with the execution model to be able to reason about properties specific to smart contracts. And also, which I didn't tell you much about, or at all maybe, we have an extraction from, so we can develop smart contracts also in Koch and extract afterwards in a functional smart contract language. So we have like a prototype implementation of that. And as a future work, we would like to sort of extend the meta theory of the language we formalize. So to add some static semantics and type soundness, so our embedding also preserves soundness types. Also to add gas analysis, this is an important feature. I didn't talk about that much, but this is something that's used for smart contracts to sort of measure as a measure of computational efforts, and also to ensure that all the contract executions terminate. So we'd like to add gas analysis also to, I mean, we have all the machinery essentially. So this is just requires sort of a bit more work. And we would like to connect it to a Certicock, providing a sort of efficient way of execution for executing contracts written in our framework, but through the sort of a certified compilation chain all the way down to low-level code. Yeah, this is it. Thank you.
Questions?
So, of course, you mentioned the famous DAO bug, and everybody says that's why we need to verify things. But the key ingredient there that I've not seen yet, which I think is very important, I've puzzled over it, I haven't come up with anything yet, is what you need is some property you'd like to verify of contracts in general, that if you'd verified that property, something like the DAO bug couldn't exist. And more importantly, right, there's lots of work people have done about, oh, look, this thing finds the DAO bug once they know about it. Right, but what you want is a general property that would have caught the DAO bug before you knew what it was. Right, that's what we're really missing. So do you have any ideas about how to do that?
I can comment a little bit. So basically, here with this execution model, so it's a little bit different from, say, Ethereum, right, where it was written, the DAO contract. So if you follow this execution model, and if you sort of confine everything, if you know that if you confine everything to this function, so for example, you do not schedule any self calls, and so you basically emit only transfers afterwards. So I think you can prove something that the reentrancy will never happen. So here you actually have to be clever how to encode the reentrancy so to be exploited in this execution
But of
model.
course, that presumes that you know reentrancy is bad, which we only knew after the DAO bug.
Yes, I think here, I mean, you have more sort of control over the, maybe if you sort of limit the actions which are emitted here by this one-step contract execution, you actually can prove that less bad things happen. So I can't say, well, exactly how to do it, but I think in this execution model, that might be possible to say something about that less bad thing can happen in an easier way than at least for something like Ethereum. That's, I guess, what I can say.
Okay, completely different point. You're using an account model like Ethereum, and
Account model, yes.
right. At Cardano, we use something different, which
Yes,
is the EU
unspent
TXO
tokens,
model.
yeah.
Do you think what you're doing would adapt to that?
Well, I mean, yeah, it's a good question. I mean, here this scheduler is something that tailored particularly to handle this account model, I think. I guess, I mean, the part of this framework which comes before the scheduler, I think this can stay the same for other ways of like unspent transaction outputs, for example. So I guess just changing so that the bits you go about executing emitted transactions that might also fit to a different execution model as well. I hope so.
Okay, thanks.
More questions? So I have a general question.
Yep.
You are not the only people doing formal verification of contracts.
Oh no, yeah.
Would you care to venture a guess how much actual money has been saved by formal verification efforts so far?
It's an interesting question. If people counted that? I mean, the only sort of information I usually see is how much people lost due to the hacker attacks. Yep. So it's not that much information how much was saved. Well, I think we are going there. I mean, this is effort slowly sort of being sort of accepted to industrial applications. So I don't have this information yet, but hopefully, I mean, will be more and more sort of more robust implementation of smart contracts and less hacker attacks. So yeah.
Okay, let's take a break. The next session starts at 11:45.
I think the next